So we want to talk now more about acid-base strength. What makes a strong acid? What makes a weak acid? And how do we determine that? Because it's not something we can really just, say this is a strong acid or this is a weak acid. Why not? Well, how many of you have ever worked with sodium hydroxide? And why do I ask about that? Well, if you've ever worked with sodium hydroxide, what does it look like? And is it easy to handle? So that's a picture of some sodium hydroxide. It's a white solid, and if you leave it sitting around it just out in the air in the room, it'll still be there days, weeks, months from now. Now, the reason we're going to need to define mathematically what we mean by a strong acid or a strong base, to me, is best illustrated by the following story. So this story dates back almost 10 years now, but it was a group of students who was taking both analytical chemistry and organic chemistry. And the way their schedule was they had a 1-hour analytical chemistry lecture at about 12 o'clock. Then from about 1:30 to 5, so that was 12 to 1. Then 1:30 to 5:30, they had a 4-hour analytical chemistry lab. They had an hour off for dinner, and then they had about a 2.5-hour organic chemistry lecture. And they did that once a week. And the reason I tell you this story is I had a bunch of students come up to me confused one day, because there were 3 or 4 students who had this schedule. And they said they were going into their analytical chemistry class, and they said Dr. Kowalczyk, who was the professor of that course, was telling them that sodium hydroxide is a strong base. And he had just told them that again that day. But then some of them asked in that course, they said, well, we're getting confused because we go to organic chemistry at night, and in that class, Dr. Kowalczyk tells us that sodium hydroxide is a weak base. So who was right? Well, that's the bad thing. Both of us were right. It all depends on your context. For an analytical chemist who works mainly in water, sodium hydroxide is not only a strong base, but the strongest base you can have. But for an organic chemist, we commonly work with much stronger bases. And let's see an example of that. So in this video, you're going to see a base known as Tert-Butyl Lithium. And everything you see in this video is real. This is a base I've worked with many, many times in my career, so there's nothing exaggerated about this video. But just go ahead and watch and see how the Tert-Butyl Lithium behaves. So in fact, this first part of the video, you can see the bottle of that he was using probably wasn't very good anymore because it didn't do a whole lot. One thing to notice here is if you notice, well, that wasn't quite what we wanted to do. But if you notice up at the top of the bottle, right where I've paused it, there's a septum there. In other words, this bottle is actually completely sealed. You can't let any air into it. Why not? Well, what happens if you expose this chemical to air? That's what we're going to see. And so yes, Tert-Butyl Lithium is such a strong base that if you even expose it to air, it will spontaneously catch on fire. So for an organic chemist, that's what we would define as a strong base. And so the message I'm trying to get across here is, are these terms strong and weak, even though we use them all the time? And I'm sure that I will use them many times. That being said, they're all relative. So what we really need is a quantitative way to measure acid-base strength. And so we do that by looking at the degree of dissociation. Which is what Arrhenius originally said to look at. The problem with Arrhenius is that Arrhenius defined a strong acid as one that completely dissociates. But if you think about what we learned in the equilibrium chapter, we know that nothing truly ever completely dissociates. So here's the generic reaction for an acid with water. And we can write an equilibrium expression as A minus, which is our conjugate base, times our conjugate acid H3O plus over HA, which is our acid, times the concentration of water. Now, what we're going to do is multiply both sides by the concentration of water. And so we get Kc times the concentration of water is equal to H3O plus times A minus divided by HA. Now, why did we do that? Well, we're assuming a dilute solution. One where it's mostly water and just a small amount of the acid. Well, if we do that, then the concentration of water is constant, or roughly constant, close enough that we don't need to worry about it. And so we define this new expression now, our equilibrium constant times the concentration of water, or H3O plus times A minus over HA. We define this as Ka, or the acid ionization constant. Now, what does this tell us? Well, if we have a weak acid, then that means it's not going to dissociate very much. So our concentration of HA will be much larger than our concentration of A minus, as well as H3O plus. Or we would have a small number up here divided by HA, a much larger number. And so overall, what will that make the value of Ka? Will it make Ka small or large? It will make Ka very small. What about a strong acid? Well, in a strong acid, that's going to dissociate to a large extent, and so our concentration of A minus will be much larger than our concentration of our initial acid. And that means Ka will be large. And so we could look at some typical acids and we can look up their Ka values. Something like HCl has a Ka value of 10 to the minus, not minus, but 10 to the 7th. Hydrochloric acid, or hydroiodic acid, 10 to the 10th. Acetic acid, what we find in vinegar, that's a little bit weaker, 1.8 times 10 to the minus 5th. And you can even measure Kas for things that you wouldn't necessarily think of as acids. Something like methane, 10 to the minus 60th. The only problem is we don't really like working with these numbers because Kas can range anywhere from 10 to the minus 60th to 10 to the 30th. And so instead, we use what's known as a pKa, where we calculate that by taking the negative log of Ka. These numbers then become much easier to work with. So for something like HCl, we get a pKa of minus 7, minus 10 for HI, 4.76 for acetic acid, and approximately 60 for methane. So when we're dealing with pKa, a large pKa is actually a weak acid, and a small pKa would be for a strong acid. It's also extremely important to remember that this scale is a logarithmic scale. And so even a difference of 1 or 2 in pKa, so if we're talking about HCl, pKa of minus 7, HI, pKa of minus 10, this is approximately a 1,000 times difference, because for each one, it's basically 10 times. Another reason that we saw the example with the bases that showed us why we need this, but it's also just as true for acids. So many of you, if you've taken a chemistry course before, may have worked with something like hydrochloric acid. And you were probably told that hydrochloric acid is a strong acid. And the truth is, it is a strong acid. But you can see already that we have HI, which is close to 1,000 times stronger. But then we have acids that make even HI look weak. So this compound here, and that is the actual name of it, is known as magic acid. Magic acid has a pKa somewhere around -23. So we're talking about even 1,000,000,000,000 times stronger than HI. And so that's why it becomes so important to have these numbers and that we can talk about these relationships mathematically. Because without it, we just end up using these highly ambiguous terms. Biggest negative, though, with magic acid is the following. It's expensive. A 25-gram bottle runs somewhere around $270. So not something we use all that often. Now, how do we measure base? So that's how we measure acid strength. What about base strength? So the logical guess might be pKb. Now, it turns out pKbs exist. But if you go searching for them, they're actually really, really difficult to find. And the reason is because nobody uses them. Why is that? Well, let's look at the following. So here's a pair of acid-base reactions. And the reason I've chosen this reaction is this pair is a pair of acid and conjugate base where I can easily find the pKa and pKb. So HOCl has a Ka of 3 times 10 to the minus 8. Whereas OCl minus, hypochlorite, has a Kb of 3.3 times 10 to the minus 7. Now, given that this is a conjugate acid, conjugate base pair, should there be a relationship between their Ka and Kb values? We know that a strong acid leads to a weak conjugate base, but will there also be a mathematical relationship? Well, if we add the two equations together, we end up with a total of 2 water forms H3O plus hydroxide. To get the new equilibrium value for this combined equation, we have to multiply the two equilibrium values that we added together. So the new K for this reaction is going to be Ka times Kb. And so what this tells us is that if Ka is large, so again, the equation we got here is K equals Ka Kb. And it turns out you can prove this mathematically. We don't need to. But this is always equal to 1 times 10 to the minus 14th. And so if Ka is large, then Kb has to be small. Or in other words, they're inversely proportional to each other. You could also redo this in terms of pKa's. So you could take the negative log of Ka, Kb is equal to the negative log of 1 times 10 to the minus 14. So our right side will just be equal to 14. And remember, if you add two things that are inside a log, that becomes the same thing as adding their logs together. So this becomes pKa plus pKb is equal to 14. So there's always an inverse relationship between pKa and pKb. So we don't end up needing two separate scales for it.